Okay, so we are talking about pumping lemma. So, in the last class we have we have defined the pumping lemma, like what is the pumping lemma. This is just to recap, this is a necessary condition to be a language to be a regular language. So, given a language L, which is a subset of, sir, if this is regular, suppose this is regular set or regular language, then we have seen that regular means there has to be a DFA which is accepting this language, any member of this language must be accepted by this DFA L, and the size of this is n. So, this given this L, the language, if it is regular, then what we have? There exists a n. This n is nothing but this cardinality of this set Q, there is n number of states. Then, if we choose a string which is more than n from L, if we choose a string whose length is more than n, like this, say we are choosing a z of length n, which is greater than or equal to this n. Then we have seen this z can be written as a1, a2, aj, then aj plus 1 to ak, then ak plus 1 to an. This is our u, this is v, this is w, such that the delta hat of q 0 z, this has to be in one of the final state. So, this is belongs to f, then the delta hat of q 0 u v to the power w I w, this also belongs to f. I mean, this also has to be this string also has to be accepted. So, that is the pumping lemma. So, let me just write it. So, let me just write it again. So, for a regular set L, then there exists a constant n such that if we choose a if we choose a word whose length is more than n, then we must able to write z to be u v w, where u and v length is less than n and length of v has to be greater than 1. Then for every I greater than or equal to 0, this also has to be accepted by the DFA. This will also belongs to L for every I. If I is 0, this is u v, u w. If I is 1, this is L. If I is 2, then u v square w, like this. So, this is what is called pumping lemma. This is the necessary condition. If we have a L, then there has to be a there is a constant n, that is nothing but the number of states in the DFA. Then we can given any string of more than n, that is z, we can write z as this, where we will have a substring v which can be pumped like this, and that has to be again in L, that has to be that string, new string has to be accepted. So, this condition is necessary condition. If a set is regular, then we must have this condition satisfied, but this is not a sufficient condition. That means, if it is true, then for a given set, then we cannot say that set is regular. So, we will use this condition to check the non-regularity of some set. Given a set, if this condition is not satisfied, then we can straight away say this language is not regular. So, we will apply this pumping lemma to check the to check whether a set is non-regular or not. Okay, so, first example is let us take a set which is 0 to the power I square. I is an integer. I is an integer greater than 1. Is this regular? I mean, is this language is regular? That is the question. That we have to find out. We have to check it using the pumping lemma. Okay. Now, this will show. So, this is meaning this is say 0, 0, 0 1. So, 0 1. So, 2 means 0 0 0 0. 2 means it is 4 like this. So, these are the string. So, this is the string of 0 with length perfect square. String of length 0, this is any string of length 0. If this is k, then k has to be a some n square, perfect square. That is the set. Now, this set is we have to show whether this is regular or not. So, suppose this is regular, if possible, or suppose L is regular. We will prove using contradiction. Then if L is regular, then it must satisfy the pumping lemma, that is the necessary condition of a regular set. Then we must have then there exists a n, which is nothing but the number of state in that DFA. There must exist a n such that if we choose a z from this L whose length is more than n or more than equal to n, then z has to be written as u v w, where u v are less than n, then this u v to the power I w has to belongs to n for all I. Okay. So, now let us check that whether this is possible or not. So, we take we have to take a z which is more than n. So, let us take length n square. Say we take z equal to this n square. So, obviously, mod of z is less than mod n, mod of z is less than n. Okay. Now, if we write this as u v w, where so these are all zeros, this is all zeros where length is n square. Now, if you write this as u v w, where u and v are less than n, then what will happen? Yeah. So, this is the n square. Okay. Now, this is u v w we are writing. Now, if we take, then all the u v to the power I w has to belongs to L. Now, if you take I is equal to 2. So, in particular this has to be in L. Now, what is this? So, if you take u v square w, then this set length of this set. So, these are all zeros, that is no issue, but only thing length of this has to be a perfect square. Now, what is the length of this? Length of this is nothing but length of u v w plus length of v, because we have added only one v square this is. So, length of v. Now, length of this is n square and length of this is less than n. Okay. So, that means let me just do it here. So, that means length of u v square w is less than equal to n square plus n, which is less than n plus 1 whole square, and n square is less than this, because we have added u, n square was the length of u v w. So, now this has to belongs to L, because that is the necessary condition from pumping lemma. So, for that this has to be a length of this has to be a Sparks-Peck square, but that is not possible. Why? Because it is lies between length of this is lies between n square and n plus 1 square. There is no number over here which can give us the length of this to be a Sparks-Peck square. So, that is the contradiction. So, that is the contradiction, that u v square w does not belongs to L. So, this is the contradiction. So, by pumping lemma we can say this imply L is not regular, straight away we can say that. This is the use of pumping lemma. We can straight away say L is not regular. Okay, we can take another example. We will check 0 to the power n, 1 to the power n, this we have seen earlier also, where n is greater than equal to 1 is regular or not. This is sigma is 0 1. Okay. So, we have to check whether this is regular or not. So, again by similar way, suppose this is regular, suppose L is regular. Now, if L is regular, then there has to be a n, we fix that n, such that if you take any string from this L whose length is more than L, that Z, then there has to be an n, there exists a n, we fix that n, which is nothing but the number of state in that finite state machine, we fix that. Now, if we choose a Z whose length is more than n, suppose we choose Z to be this, whose length is 2 n. So, it is more than n. So, length of this is 2 n, which is more than n. Now, Z has to be written as u v w such that mod of u v is less than n and mod of v is greater than 1, length of this mod means length. Okay. And this is true for all such Z where length is greater than n, that fix n. So, now this pumping lemma is telling us u v to the power I w must also belongs to L. So, this we have to check, and this is true for all I. So, this we have to check whether this is happening for some I or not. Okay. So, how to check that? So, let us let me write it here. So, Z is 0 to the power n, 1 to the power n, which is u v w. So, u v is less than n. So, that means u v is of the form. So, u will be 0 to the power I, something like that, and v will be 0 to the power j, like this. Okay. And w is having w is so 0 to the power n minus 0 to the power n, no, one part is there. So, 0 to the power n minus I minus j or I plus 1 and 1 to the power n, this is our w. But anyway, we are not much worried about w. Now, if you take some I, say I is equal to say 0, then what is this expression? u v to the power I w. So, I is 0 means this is missing, this is u and w. So, this is nothing but this is nothing but 0 to the power n minus j 1 to the power n, and this is supposed to be is n, but this is not of the form 0 to the power k 1 to the power k. So, that means this does not belongs to L, because L is of the form 0 to the power n 1 to the power n. So, that is the contradiction. So, this has to be true for all such strings. So, this is the contradiction. By pumping lemma we can say L is not regular. L is not regular. Okay. So, we can have some more example also. Yeah. So, we can have, so this 0 to the power n 1 to the power n is not regular. So, there is we do not have any DFA which will accept this. Why it is true? This is not regular, 0 to the power n 1 to the power n is not regular. That means, there is no finite automata which will accept this. This we have seen by pumping lemma, but there is another way we can convince this, because this is what? This is accepting all the string which is number of zeros is same as number of ones. Number of zeros is followed by number of so first we have number of zeros 0 0 0 something and 1 1 1 something. So, now this number is same, but in the automata, finite automata so far we have seen has no way we can just store this number. How many times we have encountered a 0, how many times we have encountered 1. So, that is not so far we have seen. So, we do not have memory there. Okay. Anyway, we will talk about this on more details when we talk about push down automata. Okay. Similarly, we can prove this also, 0 to the power n, 1 to the power n, 2 to the power n, here n is greater than 0 is not regular. Is not regular. So, how to prove this? So, similarly we can prove this. So, suppose this is regular, then there exists a n such that that n is the number of state in that finite automata, such that if we choose a z which is length is more than n, then z we can write is as this, then u v to the power I w must belongs to L for all I. So, this is the necessary condition of a language to be regular. Now, here we can choose this, suppose there exists a n and we choose a z, suppose there exists a k, n may be k, but we can take n also, does not matter, or we can take p, this is called pumping length. Okay. Then we p is nothing but the number of state of that automata which is accepting this. So, we are assuming this is regular. So, now we have to choose a z which is more than p. So, if you take 0 to the power p, 1 to the power p, 2 to the power p, so this length is more than p, 3p which is more than p. Okay. So, now we should have this, we should have what? We should have u. So, this should be written as u v w, where mod of u v must be less than p and mod of v must be greater than 1. Okay. Now, in this case, so u will be of the form 0 to the power I or 0 to the power say yeah, I v will be of the form 0 to the power k j and w is like this. Now, we know u v to the power I w for all I greater than equal to 0 mass belongs to L. Now, in particular if we take I is equal to 0, this is u w, mass belongs to L. So, what is u w? U w will be 0 to the power I and w is nothing but w has p q also. So, some 0 part will be there, 0 to the power p minus I plus j 1 to the power. So, this if we add it out, it will be, yeah, it will be 0 to the power p minus j and then 1 to the power p 2 to the power p. This does not belongs to L, because L is has to be of this form this. So, there is a contradiction. If it is a regular language, this has to be belongs to L for all such things, all such I. So, this does not belongs to L. So, this implies L cannot be a regular language. So, that is also coming from pumping lemma. Okay, so, we take some more example and we will use some properties of the regular language to show that a language is not regular. So, for example, suppose we have a language L, set of all binary string with unequal number of zeros and ones, with unequal number of zeros and ones. Okay. So, this will show this is also not regular set, this is not a regular set. So, how to show this? Either we can directly apply the pumping lemma or we can show using some properties of the regular set. So, what is the complement of this? Set of all binary strings whose length of zeros and length of ones are not equal. So, what is the complement of this? So, complement of this is nothing but length are equal, okay, and we know this is not regular. Just now we have seen, we know this is not regular. Then this implies L is also not regular, because if L is regular, then L prime is complement is also regular, that is the property we have seen. So, that is the contradiction. So, if so this is the, sometimes we do it by this way instead of directly going to the pumping lemma. We know some result, we know this is not regular and this is the complement of this. So, then this will be also not regular. Okay. So, we take another example. Okay, say suppose we have some language L which is nothing but 0 to the power m 1 to the power n, where m not equal to n. M not equal to n. So, now we want to check whether this is regular or not. So, now we observe that complement of this intersection with this set this is this. Okay. Now this so now we are looking for whether this is regular or not. Now we know this is not regular. and then if this is regular, if this is regular, then this has to be regular. Okay. So, but from the pumping lemma we already know this is not regular. This is not regular. So, from here this cannot be regular. Cannot be regular, because if this is regular, then this will also has to be regular, because this is regular. If this is regular, then this will be regular, and this is the regular, this is regular. So, then we know the intersection is also regular. So, this has to be regular, then this will be regular, but we know this is not regular. So, this is not regular. So, this is the otherwise we could directly try to prove using pumping lemma. So, these are the example. In the lecture note there will be more example on this using the pumping lemma to show the a language is not regular. Thank you very much.